Hello, I'm Zeinab, and I'll be talking about my poster, Mechanism of Temporal Interference Stimulation, in the next 3 minutes. Temporal interference stimulation is a method that has been recently introduced to brain stimulation in order to target deep brain regions. In this way, we have two sources of stimulation in kilohertz range that are slightly different from one another in their frequency component. In that way, it can produce amplitude modulated waveform where these two sources intersect with one another, while the cortical areas would be exposed to purely sinusoidal waveforms. Human head models shows that amplitude modulated component can target deep brain regions. However, cortical areas are exposed to purely sinusoidal waveforms. In this study, our goal was to develop an experimentally constrained theory to explain temporal interference's sensitivity and selectivity, meaning first, how much current do we need in the scalp in order to modulate deep brain regions, and also why central nervous system is sensitive to amplitude modulated waveform, but not purely sinusoidal. With that, we used a slice hippocampal recording, which has been exhaustively used in neuroscience. Here, gamma oscillation has been generated using carbocol, and also we used a computational network model using adaptive exponential neurons in an excitatory inhibitory network in order to explain the results that we see in our experiments. Now let's jump to the results. Here we use 5 Hz sinusoid as a control, which has been reproduced in the literature several times. And then we move to test the amplitude modulated waveforms with 1 kHz carrier frequency here, and also the purely sinusoidal. Here, the spectrogram shows that amplitude modulated waveform can modulate the gamma oscillation, but with higher intensity, pointing out to the low-pass filtering properties of the membrane. And also another thing that I want to draw your attention to is that here in amplitude modulated waveform, in the areas that amplitude modulated stimulation goes back to 0, the power of gamma oscillation doesn't go back to its baseline. It's below the baseline, which points out or suggests some adaptation mechanisms. In a purely sinusoidal waveform, we have the same behavior. At the beginning, we have this huge response, then it damps, again, suggesting adaptation mechanism as well. Here, I have quantified all the experiments in the gamma power, which is normalized to their baseline power that we can see from 5 Hz to 100 Hz and 2 kHz. From going from 5 Hz to 100 Hz, the profile of the response is different. And from 100 Hz to 2 kHz, we can see the profile is the same, but in order to produce the same results, we need to increase the intensity, pointing out to the low-pass filtering properties of the membrane. Now, on the bottom, we can see amplitude modulated waveforms with different carrier frequencies. From left, we have amplitude modulated waveforms with 100 Hz, 1 kHz, and 2 kHz. We see all the behavior is the same. The only difference is from 100 Hz to 1 kHz, we need to increase the intensity in order to produce the same results. And also, this quantified gamma power shows us again that the time that amplitude modulated waveform is going back to 0, the gamma power doesn't go back to its baseline, again, pointing to the adaptation mechanism that may be involved in our experimental system. This is the summary of all the experiments that we have done so far, and it shows that the sensitivity drops with increasing the carrier frequency, and our computational model reproduced the experimental results. We learned 2 important lessons here in this study. One was the selectivity of the network that we use in our experiment. was governed by the adaptation mechanism that was in our models. We modeled it using GABA B inhibition, and also the sensitivity was governed by the time constant of the network and its highly sensitive compartments. If you're interested to learn more about the study, you can check out our paper in bioRxiv, and also you have access to our data that is available online on the open source frameworks. Thank you for your attention.